Love you like a related rate.
But what's a related rate?
I'm glad you asked, honey.
Hi, I'm Chandler Householder.
And I'm Isabel Robinson.
And today we'll be talking about related rates.
Related rates are when two or more variables are changing with respect to time. So to solve a related rate problem, we need to recall implicit differentiation, chain rule, and don't forget that it's in respect to time when you do your derivatives.
Alright, so here we have drawn out and written out the given variables for the first problem in your notes. You can go ahead and follow along. And so this problem states that a police cruiser approaching a right-angled intersection from the north, right-angle intersection, is chasing a speeding car that has turned the corner and is now moving straight east. So, fugitive police car. Alright, so when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determined with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? And so let's go further into the various numbers they give us. So it tells us that the cruiser is 0.6 miles north. So that indicates that this distance, y, is equal to 0.6. And then we are given that the fugitive car is 0.8 miles to the east. And so that gives us the x value. Also, the problem tells us that according to a radar, that the z, or the distance between them, is changing at 20 miles per hour. And so we know this is a rate, as indicated by dz dt, because it says miles per hour. And so that is an analysis of what this problem is actually giving you, which gives you a basis of how to work with it.
Alright, so now that we have our givens, we can think about what equation we need to use to solve this problem. And the most obvious one is the Pythagorean theorem. So what we do is we take this equation, but we know that's not enough. We can solve for z. But that still doesn't give us what we need, which is dx dt. So what we do is we're going to take the derivative with respect to time. So just remember our implicit differentiation rules and apply those to all variables. So for example, x squared would become 2x dx dt, y squared is 2y dy dt, and z squared is 2z dz dt. So now that you can see that we're given dz dt and dy dt. So all we do is solve for z, and then we plug all the things that we're given, and we eventually will find dx dt.
Alright, so now that we have a good grasp on the problem and what's actually going on, now let's get into the nitty-gritty number crunching part. Alright, so we're starting with the Pythagorean theorem to get z, so we can later plug it in. So we're given y and x, so x is 0.8 squared plus y being 0.6 squared equals z squared. And so if you punch that into your calculator, you will get that 1 is equal to z squared. Therefore, square root of 1, z is equal to 1. And so now, all we have to do is plug it in to that implicit differentiation. And so, just to start from the beginning again, to show that we're using just the same equation the whole time, I'm going to rewrite it. So now we use implicit differentiation, getting us and from there, it's just a plug and chug problem. And so then, if you go to punch it into your calculator, you get that dx dt is equal to, ding, 70 miles per hour. And so that is how you solve related rate problems dealing with changing distance between two different variables. All right, so whereas previously we worked with a related rates problem dealing with two cars and changing distances, it can also be applied to situations with, let's say, a water level rising or falling, and in this example, in a conical container. All right, so in this problem, which I believe is the third example in your notes, it says, water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Alrighty, so now that we know kind of what the problem is about, let's analyze our givens. And so it tells us that the maximum height of the conical tank is 10 feet and that the maximum radius is 5 feet. Now, this is key when looking at our initial equations we can plug it into before our implicit differentiation. And so this also is crucial when applying it to a common relationship in all cones, which is between the radius and the height, that they will always have the same proportions, which is why we need the equation r over h is equal to 5 over 10. And so in this situation, we would be using a height of 6 feet. And then lastly in the problem, it gives us that the rate of volume is changing at a rate of 9 feet cubed per minute. And so this is also very important to plug in to this equation, which we're all very familiar with, which is the equation for the volume of a cone. And so once we do our implicit differentiation, we're able to plug this in here, rearrange this, and put it into here. And so that's a good grasp onto how to begin solving this problem.
Alright, so what we want to do now is find the relationship between these two cones. Basically, it's just a smaller cone inside a bigger cone. So we know that 10r equals 5h when you cross multiply this relationship. And so from that, we can get r equals 1/2 h. From here, square each side so you can plug that into your volume equation and be left with one variable. So here we can get VH equals 1/3 pi, plug in this for this, and you get pi h cubed over 12. So now we can set up an equation here by taking the variable. So we get dv dt equals 3 pi for 12h squared times the h dt. And it's very important to remember that since you're doing implicit differentiation, you need to take the implicit derivative for each side, no matter what, no matter which variable. Right, so from here, we can get 9 equals pi over 4 times 36 dh dt when you plug in your givens. And then from here, you get 1 equals pi dh dt. Can change that to 1 over pi equals dh dt. So your final answer is 1 over pi feet per minute. Do you get it now, babe?
I do understand it a lot better, but I could use a little bit more practice.
Well, it's a good thing I've written 5 more homework problems for you. Check it out and get some more practice. And good luck with related rates.